Alrighty, so in this video I'm going to be going through the section B of January 2010 Unit 4. So let's get started straight away. So question 1a. Describe the energy changes that take place as the bob of a single pendulum makes one complete oscillation starting at its maximum displacement. So initially the object has gravitational potential energy, or GPE, because it's at its maximum displacement, and then that's transferred fully to kinetic energy at the equilibrium position, and then back to GPE when it reaches halfway through a cycle, and then that goes back to kinetic energy when it's coming back, and then finally ending up as GPE. So it says during one complete oscillation, so you should be essentially having the same energy transfer twice. Okay, so we've got a girl on a swing we're modelling as a simple pendulum. We're doing 15 oscillations, took 42 seconds. Calculate the distance from the top of the change to the centre of mass of the girl, giving your answers the right number of significant figures. So the first thing we need to do is work out what the time period is. So that is going to be 42 divided by 15. Let's keep it as a fraction for now. And we know that the time period is 2 pi root L over G, which means that L is going to be T over 2 pi squared times by G. So let's substitute the numbers that we have there. So time period 42 divided by 15, divide that by 2, divide that by pi, all squared, times by 9.81, gives you 1.94822. We've got two significant figures in the answer, so we would give that as 1.9 meters as your final answer, because the numbers in the question were to two significant figures. Moving on. To set her swinging, the girl and seat were displaced from equilibrium and released from rest. The initial displacement of the girl raised the centre of mass of the girl and seat 250 millimeters above its lowest position. The mass of the girl was 18 kilograms. What was her kinetic energy as she passed through this lowest point? So the change in the GP, which would be converted into kinetic energy, is going to be the mass times 9.81 times by the change in height minus 3. That's going to give you the kinetic energy, so 18 times 9.81 times 250 times 10 to the minus 3 gives you 44.145. So it's just going to be 44 joules to two significant figures. So maximum speed would correspond to this. So we know that half mv squared equals kinetic energy. So we know that v is going to be 2ke over m square rooted. So let's put that 44.145 times by 2 divided by 18 square rooted gives you 2.21 is 2.2 meters per second. There. Alright. On figure 2, draw a graph to show how the kinetic energy of the girl varied with time during one first complete oscillation, starting at the time of her release from maximum displacement. On the T represents the period of things, so we're going all the way through one full cycle. Okay, so at maximum displacement, kinetic energy is 0, so you'd have a point here, and then we have at t over 2, it would be back at 0 again, because it's at the other end, and then at t it goes through 0, and then during these we'd go through various different places. So we're going to go up to 44 by t is quarter, so 40, so sort of like there. And we have the same point here. So essentially these are the key points that it's going to go for, so it's going to sort of look something a bit like this. In terms of its shape, so we're going to get a sinusoidal shape. Okay, so let's move on to question 2. Capacitor initially charged to PD of 6, so we've got V is 6, and it's discharged through a 100 kilo ohm resistor. Calculate the initial discharge current. So hopefully remembering from AS, V over R, so 6 divided by 100, it was 100 ohms or 100 kilo ohms? 100 kilo ohms, so 100 times 10 to the 3. So 6 divided by 100 times 10 to the power of 3 gives you 6, 0 times 10 to the minus 5 amps there. Okay, use the graph to determine the time constant of the circuit giving an appropriate unit. So we need to find what 37% is, times 6 is 2.22 volts. So let's mark that on the graph. Where's 2.22? It's about here. So let's read across. So we're looking somewhere about here. So that looks like a time of 22 seconds there if you're reading off from the graph. So that would be 22 seconds because it's a time. Hence, calculate the capacitance of the capacitor. Okay, so T is equal to RC. So C is going to be T over R. 22 divided by 100 times 10 to the 3. And that gives you 2.2 times 10 to the minus 4, or 220 microfarads, I suppose you could go for it. Show that the capacitor lost 90% of the energy it stored originally after about 25 seconds. So if it's lost 90% energy, it will be 10% of its original one. So you know that E2 divided by E1 is equal to 0.1, and which means you know that V2 over V1 is going to be the square root of 0.1, because if you remember, E is proportional to V squared. So if the ratio E2 over E is 0.1, V2 over E1 will be square root of 0.1, which is 0.316. So suppose that V2 is going to be that times by 6, 1.89 volts. That's our predicted value. Read from graph at 25 seconds. Looking at the graph, that looks like it's about 1.9 volts, so it has lost 90%. So just to explain what we've gone through, so we've worked out this is the ratio of the predicted ratio of the energies, which gives you this predicted ratio of the potential differences. Multiplying this ratio by V1, which was 6, gives you a predicted V2 at which 10% is lost. Reading from the graph, we get after 20 seconds is 1.9. There's a similar value, so we know it's correct and it's worked. Okay, in order to reduce the time delay, an intrude alarm contains a capacitor identical to the capacity used, and the capacitor is charged from a 12 volt supply instead. So it's very similar. State and explain the effect of this higher initial PD on the energy stored in the capacitor. So the energy stored is proportional to V squared. We used that in the last question. So if you double V, energy is going to be multiplied by 4 because it's V squared. State and explain the effect of this higher initial potential difference on the time taken for this capacitor to lose 90% of its original energy. So essentially we're looking for the condition, the time at which we get this, because we want the time for it to be 10%, so we'd actually cancel the V's. So we actually find that the time is independent of the potential difference initially, so no change. Alright, moving on. Okay, state the relationship between gravitational potential energy and the gravitational potential for a body of mass m placed in a gravitational field. So the potential energy is just the mass m times the potential, essentially. So that's the relationship between them. What is the effect, if any, on the values EP and V if mass m is doubled? Potential energy is proportional to the mass, so it's going to double the potential energy, but the V is independent of the mass in the field, so that's going to be no change. We've got two orbits A and B, which can be occupied by a satellite. Gravitational potential due to Earth of each of these orbits is given. So, okay. Calculate the radius from the center of the Earth of orbit A. Okay, so if we think how we calculate potential, it's minus gm over r, which means that r is minus gm over v, which is minus 6.67 times 10 to the minus 11. And dig into our formula sheet, we've got 5.98 times 10 to the 24 divided by minus 12 times 10 to the 6. So let's put that into the old calculator. 6.67 times 10 to the minus 11. It's 5.98 times 10 to the power 24 divided by 12 times 10 to the power 6. And that gives us, in standard form, a value of 3.3 times 10 to the 7 meters. Okay, so we want to show that the radius of orbit B is approximately 1.1 times 10 to the 4. So, first of all, from the data previously, we know that VB is 3 times VA, and we also know that potential is inversely proportional to 1 over r. So we know that essentially then that the radius of B is going to be 1/3 of that of the radius of A, which is 3.3 times 10 to the 7 divided by 3, which is going to be 1.1 times 10 to the 7, which is approximately 1.1 times 10 to the 4 kilometers. Calculate the centripetal acceleration of a satellite in orbit at B. Okay. So we can calculate essentially we want to know what the field strength is, which is going to be Gm over Rb squared. So we have 6.67 times 10 to the minus 11 times 5.98 times 10 24 over 1.1 times 10 to the 7 squared, which is, let's calculate it, 6.67 times 10 to the minus 11. 5.98 times 10 to the power 24 divided by 0.1 times 10 to the power 7 squared, and that it comes out as 3.296. So that's just going to be 3.3 meters per second, because the centrifugal acceleration is just going to be the acceleration due to gravity, which will be the field strength. Show that the gravitational potential energy of a 330 kilogram satellite decreases by about 8 gigajoules when it moves from orbit A to B. The change in potential energy is going to be the mass times the change in potential. So it's about 330 times by, what values do we have? We had minus 12 minus 36, and we type that in, so it's effectively 36 minus 12 times 330. Oh, and I forgot to, and then times 10 to the 6 because it's in megajoules, times 10 to the power 6, which is 7.92 times 10 to the 1, 2, 3, 4, 5, 6, 7, 9, which is approximately 8 gigajoules. Alright, explain why it is not possible to use the equation delta EP equals mg delta h when determining the change in gravitational potential energy of a satellite as it moves between orbits. So mg delta h relies on g being constant, which it is not in a radial field. Which it is in this example. So we're dealing with a radial field. That's an equation for a uniform field, so we can't use it. It's fairly straightforward. Okay, outlining the essential features of a step-down transformer when in operation. So we're going to need a higher number of turns on primary side because you want it to step down side, and an alternating current or AC input on primary side. Transformers don't work with DC, so higher turns on, and we need an AC input. Describe two causes of the energy losses in a transformer and discuss how these losses may be reduced by suitable design and choice of materials. Okay, so this is a very friendly 6-marker question, something you should all know about with this here. So, one of the sources of loss is heating loss in coils. So the coils have current and they have resistance, therefore you're going to be dissipating some energy as heat. As coils have resistance, but this can be reduced by having low resistance windings. So that's going to be one of your sources, and you might, for instance, want to use a copper, and we know if we make it have a large cross-sectional area, that reduces the resistance as well. So going for a thick copper wire. Okay, so another source of energy loss is during the magnetization process. which means it takes energy to set up the magnetic field. Or to use the fancy terminology, it takes energy to magnetize or even demagnetize, I suppose, the core, and this one's reduced by your choice of material by using, it's called soft iron core, and soft means it's easily magnetized, and iron's a very typical example of that. They only asked for 2, but I'll talk about a few more. Eddy currents induced in coil due to constantly changing magnetic field, so eventually got induction. Field. Sorry, my handwriting's getting a bit messy. Laminate. You want to laminate the core, and that has the effect of essentially increasing the resistance. And which reduces the eddy current. So essentially they are less effective, and those are going to be essentially your key sources of loss in your transformer. So now I'm going to do some calculations by the looks of it with transformers. So we're looking at standby mode, so essentially when the TV is wasting energy when you're not watching it. So it says during standby mode you've got an output current of 300 milliamps at 9 volts to the circuits. How much are we wasting? So power equals IV, so 300 times 10 to the minus 3 times by 9 gives you 300 times 10 to the minus 3 times by 9, 2.7 watts of wasted energy in standby mode. If the efficiency of the transformer is 0.9, show that the current supplied by the 230 volt main supply in these conditions is 13 milliamps. So we know that 0.9 V1 I1 is going to be equal to V2 I2, which means that I1 is going to be V2 I2 over 0.9 V1. So we know that's 2.7 over 0.9 times 230, so divided by 0.9 divided by 230, which is 0.01304, which is approximately 13 milliamps. TV set is left in standby mode for 80% of the time. Calculate the amount of energy wasted in 1 year through use of standby mode. So let's first calculate the power in, which is going to be 2.7 divided by 0.9, which is 3.0 watts. Then the energy is going to be 80%, so 0.8 times P in times by the time, so that's going to be 0.8 times 3 times 3.15 times 10 to the power 7, which is 7.56 times 10 to the 7. So that's going to be 7.6 times 10 to the 7 to the right number of sig figs. Key thing here is getting your power input here, so because that will be the total amount of energy you're supplying that you're wasting. Show that the cost of this wasted energy is about £4 if electrical energy is charged at 20p per kilowatt hour. Okay, so 1 kilowatt hour is equal to 1000 times 600, because it's 1 kilowatt for 1 hour, which is 3.6 times 10 to the 6. So the amount of energy in kilowatt hours is 7.56 times 10 to the 7, divided by 3.6 times 10 to the 6, times by 0.2, because we want it in pounds. Okay, so divide by 3.6 times 10 to the power 6. Answer divided by 3.6 times 10 to the 6 times 0.2, which is £12.20, which is approximately £4. The power consumption of an inactive desktop computer is typically double that of a TV set in standby mode. This waste of energy might be avoided by switching off the computer every time it is not in use. Discuss one advantage of doing this. So advantage would be if you're essentially saving money. You'd also argue you're doing less damage to the environment, burning less fossil fuels, or those kind of things. A disadvantage would be you would then have a waiting time, so essentially you're wasting time while you're rebooting your computer. Maybe you're risking components breaking by constantly turning it on and off. It might take more energy to restart a computer than you save. There's lots of possible options, but you could go for any of those. They would be fine. They're all sensible. But that completes this section B.